Good morning, afternoon, or evening to folks tuning in from around the world. Welcome to the 124th episode of the IBM Qiskit Live Quantum Seminar Series. The seminar takes place every Friday at noon Eastern Time and will be hosted on this Qiskit YouTube channel. So subscribe to catch up on anything you missed, but you can only ask questions here live now during the seminar. I'm Wang, a research scientist at IBM Quantum, and I'll be your host today. In just a minute, we'll be hearing a talk by Vlad Sivak on quantum error correction beyond break-even. But before we begin with introductions, let's give everyone a couple of minutes to tune in. So in the meantime, for those who are already here, as usual, why don't you share where you're tuning in from? Yeah, we got Paul from Portland, Oregon. So while you're all responding in the chat box, I wanted to briefly advertise the Quantum Explorers program designed by IBM Quantum. It's a self-paced, game-based learning program spanning months where participants gain a solid foundational understanding and proficiency in quantum computing and some of its applications and Qiskit. So this year, the program's theme is space exploration. The registration opens on June 13th, and the program launches on July 6th, 2023. Okay, so I'll take a look at the chat now. Thanks for being here. We have Thaddeus from Rochester, New York, Paul from Oregon, Huazhong from Yorktown Heights. We got people from Germany, from Yokohama, so Singapore. So we really are expanding the globe here. So thanks for being here. I think it's time we begin. I am thrilled to roll out the latest episode of this IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. For those who are just tuning in, I'm your host, Wang, and today I have the pleasure of hosting Vlad Sivak, who will be talking about quantum error correction beyond break-even. Vlad is from Ukraine, did his undergrad at the Moscow Institute of Physics and Technology. He then did a PhD at Yale in the group of Michel Devoret. And during his time at Yale, he worked on quantum limited amplifiers, which he actually presented about for one of the first episodes of this series, I think episode 5. The link should be somewhere at the top of the chat. And so we're very happy to have him back a few years later to talk about this new project of his. He also worked on applications of reinforcement learning, the quantum control, and quantum error correction of the oscillator grid code, aka the Gottesman-Kitaev-Pressel code, or the GKP code. Now he is a research scientist at Google Quantum AI, working on the optimization of the quantum processor for the surface code. Take it away, Vlad.
Thanks, Derek, for this introduction. Nice to be back here. I think the seminar is incredibly useful for the community, so I'm really delighted to have this opportunity to present here. So thank you so much for inviting me. The topic of my talk today is quantum error correction using the grid code. Like you said already, it's also known as Gottesman-Kitaev-Pressel code. This work was done at Yale University, where I was before, and now I work at Google Quantum. So before we jump in, I want to thank all these amazing scientists from Yale who were involved in this experiment. The experiment was done in the lab of Michel Devoret at Yale, and I also want to thank our funding sources. So I only have one screen, so I don't see the chat or anything. So Derek, please interrupt me whenever there are questions.
Yep, definitely will.
Awesome, thank you. So let me describe first what kind of problem we address in this work. So here we see this plot that everyone loves, which shows the progress in the quality of superconducting qubits over the years, and more specifically their lifetimes and coherence times. And it covers a lot of orders of magnitude here. So it's really great. And there are all kinds of qubits. There are quantroniums, fluxoniums, transmons, 2D circuits, 3D, all kinds of things are on this plot. And they all have something in common, that they are based on energy levels of a static superconducting circuit. So in this sense, we can call them passive qubits. And, as an experimentalist looking at this plot, I want to fit these data points to something, and I would probably fit this to this curve. Of course, I think most people would agree with me that the progress hasn't completely leveled off, but it has significantly slowed down in the recent years. For example, we don't have superconducting qubits with tens or hundreds of milliseconds lifetimes, as you would expect if you extrapolate this curve. Given that it is somewhat expected that this curve will saturate eventually, there is a question of how can we keep pushing in that direction. And the answer, in theory, is that quantum error correction will allow us to create effective qubits that can live much longer than all of these physical components that we use to make them. And the goal of our experiment is basically to demonstrate that this could be done. So we call such error-corrected qubits active, by contrast with passive, basically to emphasize that they are not based on a static circuit. They require active intervention that would constantly evacuate entropy from the system. And so notice that everything on this plot is T1s and T2s. So these are the numbers that describe amplitude damping and dephasing channels, which affect these passive qubits that are based on the energy levels. But it turns out that when we do error correction, errors get kind of scrambled in such a way that the effective channel that describes the decay of an active qubit is not amplitude damping. So it can't be characterized by the T1 and T2. So we need to generalize this notion of a lifetime on this axis in order to be able to compare between these two categories of qubits. So to do that, we start with this thing that's called average channel fidelity. So if you look inside this equation, it has very clear meaning that we take a state, we pass it through a channel, and then we compare it using this overlap compared to the initial state. So if there is, if it's a perfect identity channel, then this would be 1. And then we average across all possible states on the Bloch sphere. And that's why it's called average fidelity. So for channels that act continuously in time, this fidelity will decay. In general, it will decay in some non-trivial way. It's not going to be just a single exponential. But to first order, we can expand it like so and define this decay rate gamma. And based on this definition, you can see that this rate gamma characterizes how the Bloch sphere of a qubit decays overall from all directions. So it doesn't give any preference to any particular axis or any particular basis. And fortunately, as Mike Nielsen showed in this paper, to measure this gamma, we don't need to sample the whole Bloch sphere. And it's sufficient to just average these 6 cardinal points that correspond to Pauli eigenstates. And then by some sort of linearity arguments, we can show that this gives a gamma for an arbitrary channel. So we can use it to describe passive qubits and active qubits in the same way on equal footing and then compare them. And one other important metric that I want to introduce here is this error correction gain. It simply compares this gamma for error-corrected logical qubits and to the best passive qubit that we can create in the system. And by the way, people often call these passive qubits physical qubits. So the break-even point corresponds to this gain being equal to 1, which means that error correction process just barely manages to create a qubit that is as good as what we can achieve without doing any error correction. All right, and so now that we have these definitions, let's look at the same plot as before, but now made for the active qubits that use error correction. So here is this survey of experimental progress in the field of quantum error correction. So x-axis is just the year of the experiment, and y-axis is the time measured in microseconds, during which the qubit can maintain an arbitrary state. So it's just an inverse of this decay constant that we just defined on the previous slide. And all these different labels, they correspond to different experiments. And there are 2 dots for every experiment. So one dot shows the lifetime of the best passive qubit in that system. And another dot shows the lifetime of error-corrected logical qubit. And the arrow goes from the best passive to active. So these experiments here are what people call bosonic error correction, because they encode a logical qubit into a state space of a harmonic oscillator. And these ones over here are the recent surface code demonstrations from ETH, Google, and China. And this is the heavy hex code from IBM. So we see that really in almost all these experiments, doing error correction doesn't actually improve the coherence, but makes it worse. And however, there are some good news. For example, this experiment with the cat code has demonstrated 10% improvement. And the focus of today's talk is this experiment here, which uses Gottesman, Kitaev, and Preskill code. And I also want to say that pretty much at exactly the same time with our publication on arXiv, there was this result from China that uses the binomial code. All right, so yeah, I want to mention another aspect here that in addition to just demonstrating some really good numbers, this is really the first convincing demonstration that coherence in a quantum system can be increased through active intervention, through classical intervention. So it's an interesting result just from fundamental perspectives. It proves that there is no conspiracy of nature that would make QEC impossible for some reason. So it is really pretty possible, and moreover, the technology that's needed to make it work is already here.
Vlad, sorry, quick question.
Yep.
You made this point that we should characterize qubits better with their fidelities rather than the lifetime, but then here you're plotting the lifetime. And so can I interpret the gains or the ratios between these lifetimes of logical to physical also as the gain in the fidelity of that metric you just showed in the previous slide?
Yeah, so what's plotted here is the rate at which this fidelity decays over time.
I see, got it, okay.
Or rather, the lifetime, which is the inverse of the rate.
Okay, I think I misunderstood. I was interpreting them more as like a T1, T2 type thing, but this is that general lifetime that you're talking about. Okay, got it.
Okay. So now let's dive in. So the first thing we need to understand is what is this GKP code. So the qubit has this basis of two states, 0 and 1. So in principle, any physical system that with a state space of dimension larger than 2 or equal to 2 can host a qubit. And in our experiment, we embed a qubit into a state space of a harmonic oscillator. And one way of doing this was proposed by Gottesman, Kitaev, and Preskill in 2001, and it's called a grid code. And we often call it GKP code as well. So in the position representation, the wave functions of the code words look like these grids of delta functions, which have a non-overlapping support. And so there is this kind of large distance between these code words, and because of this, the code has nice error correcting properties. And notice that these states are, well, they are composed of delta functions, and they are perfectly translationally invariant. So they extend infinitely far and contain an infinite amount of energy, which is unphysical. And of course, in reality, we have a large envelope, which is superimposed on this grid. And all of the peaks in this grid are finitely squeezed. So these states were created and error corrected in a few experiments before. So first in trapped ions, where the role of an oscillator is played by this mechanical motion of a trapped ion. And shortly after in superconducting circuits, where the role of an oscillator is taken by this electromagnetic mode inside of a superconducting cavity. And I want to give a special credit to this earlier work from Yale that made this conceptual breakthrough of how to realize and error correct these complicated quantum states in the lab. And this happened almost 2 decades after they were proposed initially, as you can see. All right, so now we know how the wave functions look in position representation, but I want to introduce a different representation of quantum state of an oscillator, which is based on the phase space. So phase space is this
Sorry,
space.
quick question to interrupt you there. You talked about the energy scale of these states. So for those who are maybe more familiar with the transmon style qubit, right, we know that the difference between the 0 and 1 state is order of a handful of gigahertz, and that's
Yeah.
why we know we need to cool them to some temperature, a few millikelvin. Can I apply similar intuition here? Like when you tell me that the energy scale of this packet is some energy value, can I relate it in the same way to like how much we need to cool it? Like, or where does that energy scale come into play basically in terms of the challenge
Yeah,
of
I think what you just described as gigahertz for superconducting circuits, in trapped ion case, it's in the kilohertz to megahertz range.
Mhm.
Yeah.
Okay.
It's a bit slower.
So then for these grid states, what's the energy scale that we're talking about? And how does that relate to, how perfect of a logical qubit state it is, let's say?
How does the energy scale relate to how perfect the qubit will be? That's probably a complicated mapping,
Mm-hmm.
because the lifetime of the qubit is determined by many different factors.
Mm-hmm.
But the energy scale will just set the time scale for the oscillation inside of this trap. So it's roughly sets the time scale for the gates that you can do, like the speed of operations that you can do on this qubit.
Okay.
Which is significantly slower than in superconducting circuits.
Got it. Thanks.
Yeah. Okay, so back to this phase space. So it's a 2D space with position on the horizontal axis, momentum on the vertical axis, and the state of a classical particle is described by a point on this plane. So in this example, this point sits at position 0 and has no momentum, so it doesn't move. If it had some momentum, then this point would be making circles on this plane. And actually, to relate it to this question that was just asked, the frequency of these circles would be in the gigahertz range for superconducting circuits, and probably kilohertz to megahertz, if I'm not mistaken, in the case of trapped ions. So in quantum case, we can't have well-defined position and momentum at the same time. And so this point is replaced by a kind of fuzzy circle that represents the Heisenberg uncertainty. So this thing here is called a vacuum state. It's just a state of rest of an oscillating particle. And this representation is called the Wigner function. So you can roughly think about it as the probability distribution of having a certain position and momentum. For example, in this vacuum state, there is the largest probability of finding a particle at position 0 with no momentum, and there is almost zero probability of finding a particle somewhere in this space here. And this is the Wigner function of the grid code, which does look like a grid. So here we see state 0 and different superposition states. And this grid structure means that the particle can occupy only certain pockets of the phase space, and it can never be found in these white spaces in between these blobs. And so this is experimental data, by the way, and this measurement is called quantum state tomography. And it gives us complete information about the quantum state. And so knowing this Wigner function is actually equivalent to knowing the wave function, but it's just a directly measurable thing. Okay, and now let's meet the system in which we realize this grid code. So in our experiment, this oscillator is realized as an electromagnetic mode inside of this superconducting aluminum cavity. And since most of the electromagnetic field lives in the vacuum of this cavity, this oscillator has a pretty good lifetime. Its T1 is 600 microseconds, its T2 is almost a millisecond. And we can prepare this electromagnetic mode in different quantum states. And if we want to embed a qubit into it, then there is also multiple possibilities of doing that. And the simplest way to create a qubit is just by using these lowest two energy levels, 0 and 1. So we often call such qubit a Fock qubit because these are Fock states. And in order to control an oscillator, we couple it to a nonlinear circuit. That's in our case, it's a transmon circuit. It also has pretty good lifetime and coherence. It was fabricated using this new technique that's described in that paper. And so we can also encode a passive qubit in the lowest two energy levels of this transmon. But in terms of lifetimes, this qubit is still much worse than this other passive qubit. And so in fact, From the lifetime perspective, this is the best qubit that we can create in this system, because going to any higher energy levels in the circuit will result in the enhancement of the emission rate of photons. And so the lifetime of these alternative qubits encodings will be lower. But the advantage of using the alternative encodings is that they might allow us to do quantum error correction, which ultimately can lead to a better lifetime of quantum information. And so, as I already explained, we will create this error-corrected logical qubit inside of this oscillator using the grid code. All right, and so this is our actual sample. So this is the chip that hosts this transmon. So that little thingy there is the transmon. This is its readout resonator and Purcell filter. And then this chip is inserted inside of this block of aluminum that hosts a cavity that's literally drilled inside of it. And that's how this transmon chip couples to the electromagnetic field of that mode. Then you can see all these kind of cables here that are our control lines. So there are just two of them, one which is used for the control of the transmon and its readout, and another one that's used for the cavity mode. And then this whole package sits inside this can that provides magnetic shielding. And you can see that any sort of hole in this structure is filled with this black nasty epoxy that prevents infrared radiation from getting inside the sample. And there is like a lot of these different precautions all over the place. And this is just the photograph of the lab. So this sample that I just showed you sits there inside of the dilution fridge, and it's cooled to the temperature of about 20 millikelvin. And then there is all this control electronics and some grad students running around. Okay, so that was our experimental setup. And next, I'll show the quantum circuit that we run to implement error correction of the grid code. So these lines represent the oscillator and ancilla in time, and different boxes just represent operations that we do in them. And I will explain this circuit only on a high level because I want to focus more on the big picture of what we do in experiment. But really, the devil is in the details, and all of the technical challenges of getting this experiment to run were in actually realizing this particular circuit very carefully. Okay, and so this big part here is a unitary operation whose goal is basically to map the error syndrome information from the oscillator onto this ancilla qubit. So it is some big, messy unitary, but it can be decomposed in this way as a parametrized circuit with many layers. And all these layers have the same structure, but different parameter values. So each layer consists of rotation on the qubit and this entangling gate, which is called Qiskit conditional displacement. And next, there is this measurement of the ancilla. And then the outcome of the measurement is processed in real time on the FPGA controller. And then this classical program that runs concurrently with the quantum circuit branches in two possible ways, depending on the outcome of the qubit measurement. And so this branching involves doing some real-time feedback operations that are conditioned on the measurement outcome. So this feedback involves resetting the ancilla to the ground state. And so roughly speaking, it's if you measured it in the ground state, you don't do anything. If you measured it in excited state, you apply a pulse that flips it to the ground state. And there is also this virtual rotation gate on the oscillator that allows us to cancel the spurious rotation that oscillator accumulates because of the always-on dispersive coupling with the qubit. So then we see that this whole circuit consists of these two similar-looking blocks, which we call cycles. And the full circuit corresponds to one full QC cycle. And to give you some sense of timescales, this full circuit takes about 10 microseconds. So each block here is 5 microseconds. The unitary part is 1.5 microseconds. And then this measurement, together with real-time processing and feedback, is 2.5 microseconds, and then remaining microsecond goes into doing this rotation gate and some idle between the cycles. And it's a fairly complex circuit. It has a lot of parameters in it, and we do our best to calibrate various components here. But then when you put everything together, you get a functioning circuit, but its performance is far from optimal. And so an important aspect of this work was to implement the training of the circuit parameters in situ using reinforcement learning. So we initialize the circuit in some way using the calibrations, and then we run the training for a few hours to optimize all of these parameter values and essentially to adapt them to control limitations and system imperfections that we have in this setup. And this training was crucial for the success of the experiment. And before we move on to talk more about training, I want you to take away an important little fact about the circuit. So there are two measurements inside, and each measurement is binary valued. So there are 4 possible trajectories that the system will take in one such QEC cycle. And that means that this circuit implements this Krauss channel of rank 4 with Krauss operators that are labeled by these measurement outcomes. So G stands for the ground state of the ancilla, and E stands for excited state. So just if you don't know what Krauss channels are, I'll explain that a little later, but just remember this fact because it will be useful for us.
Sorry, Vlad, can we go back? We have a couple of questions here.
Okay.
First question I have is, you have 4 different layers. Does that mapping on to be able to do this rank 4 Krauss channel, or is the 4 different layers like a hyperparameter in your?
Yes, so 4 layers could be more like, it could be 10 layers, but the channel would still be rank 4. This rank is determined by the measurements in the circuit. So we have 2 measurements, and each of them has 2 possible outcomes, and so that's why there are 4 different combinations, and that determines the rank of the channel. And then the number of layers is just defined to what degree of approximation we want to approach this exact unitary that is given to us by theorists and that realizes this error correction. So we find that 4 layers is sufficient, but increasing the number of layers could make this more precise.
Okay.
But
And
then
then
you pay the cost of additional time in the circuit and additional decoherence and so on.
I see. So some like approximate compilation here that you're doing that you can optimize layer by layer.
Yep.
And then for the position versus momentum cycles, is that strictly necessary? Could you correct for both at the same time somehow, or is it somehow like easier to compile as unitary by doing it in separate cycles like this, or linear combinations even of these position momentum corrections?
Yeah, that's a good question. I don't know if there is a more unified way without cycling between these different quadratures. It's definitely very convenient from implementational point of view, because on the FPGA, we literally run the same program, and the only difference between these 2 cycles is the phase. So it's either this or it's rotated by 90 degrees. But yeah, maybe some new future protocols that some theorists will propose will actually get rid of this sort of split.
I see.
Momentum. I don't know.
And a final question, this is coming from the audience, maybe I'll rephrase a little bit. The question is, what is this D gate? And maybe taking a step back, the question could also be seen as, like, what's going wrong with the logical qubit that you're fixing with this circuit exactly? And this D gate, I'm assuming some displacement that shifts it back and forth, but
right.
Maybe that's the bigger question here.
So the D gate is the displacement of an oscillator. So it's like a primitive operation similar to rotations of the qubit, but for the oscillators, you just displace them in position or in momentum or in any direction that you want in phase space. And then this ECD gate, which I'm actually not showing how it compiles down into these rotations and displacements, but it's a useful abstraction that inside of it has a lot of these individual rotations and displacements. And then regarding the second question of what errors the circuit is correcting, I will actually get to it later in the presentation. So let's maybe postpone it a little bit.
Cool. Thank you. I think that's it for now.
Okay. So here's just a quick overview of the reinforcement learning pipeline. So we have this artificial agent that is parameterized using a neural net. And then we sample different parameter vectors from this neural network. And they include different amplitudes and phases of all of these rotations and displacements that we just discussed on the previous slide. And then for each parameter vector, we compile the experiment, we run it, and then in the end, we measure some kind of proxy for the lifetime of the error-corrected qubit. And then we give this measurement outcome as a reward to this learning agent. And then there is an algorithm called proximal policy optimization that updates the parameters of this neural network in order to maximize this reward signal. And then once that update happens, we iterate again like this. And so here's a time budget of one iteration of such training. It takes about 15 seconds, I think. So the main bottleneck is the compilation of these instructions for the FPGA. So this experiment is actually completely programmed in Python. And then there is a transpiler that converts this Python script into the FPGA code. And this whole process is not really optimized for speed. So that's an area which in the future needs special attention because this sort of optimization is definitely going to be used pretty heavily in future experiments. But for now, the training for a few hours, it's long, but it's not the end of the world for us. Okay, and so now after this sort of high-level overview of the sample, the setup, the circuit, and all, let me explain the error correction process. So I think the easiest way to approach this is by drawing an analogy with something more well-known and familiar to people, which is a simple repetition code. So here is a repetition code of 3 qubits. So this is the logical 0 state and the logical 1. And together, they form a code subspace. And these are all different error subspaces, which are generated from the code space by applying single qubit bit flip errors. So notice that each of these subspaces has this replica of the logical 0 state. So that's this, in this subspace, this is the replica of 0 and the replica of 1. And they are orthogonal to each other and to all other subspaces. And so if we just count the states here, there are 4 subspaces and 2 basis states in each. And so there are 8 subspaces in total. And so they completely consume all state space available in this 3 qubit system. And so now how do we do error correction in this case? In one particular approach to error correction, which is called the stabilizer formalism, we need to measure these parity check operators, which are called stabilizers. So they are the parities of the first 2 bits or qubits and the parities of the last 2 qubits. And then from this measurement, we obtain an error syndrome, which in this example, it's 1, 0, because if you calculate these parities, that's what they end up being. Once we get this error syndrome, we can decide, we can infer in what subspace the state currently resides in. So in this case, that would be C1. So we can call that decoding. And then we decide what recovery operation to apply to correct this error and return the state back to the code space. And this whole process, all of these 4 items together, creates this one arrow that I'm showing here. And then, you know, if we happen to measure and find something else, some other syndrome value, then this will be this other arrow. And so from these arrows, you kind of already see how this error correction process starts looking like dissipation. And so I want to formalize this dissipation point of view a little better. So for that, let me quickly introduce this cross operator formalism, which is very useful for QEC. Now we will return to this repetition code example and just reformulate it using this new language. So anything that happens to a quantum state is called a channel, and it can be decomposed in this way. So these guys are Krauss operators, and the number of these operators is the Krauss rank of this channel. So instead of talking about density matrices, this Krauss operator formalism allows us to talk about pure states and their individual quantum trajectories. So in each application of this channel, the state is transformed in one of these ways randomly according to the probabilities that we can calculate through these equations. And the requirement that probabilities should sum to 1 gives us a certain constraint on what these Krauss operators can be. So this operator sum should become the identity. And this formalism can be used to describe anything you want, like amplitude damping and dephasing, our favorite decoherence channels, or unitary evolution and so on. But also it can be used to describe error correction. So in QEC, these indices, they enumerate all possible syndromes in the QEC circuit. So in the repetition code example that we've just seen, there are 4 possible syndromes. And so that means there's going to be 4 different Krauss operators in this decomposition. So what are these Krauss operators? Well, here is K0. So it corresponds to the syndrome, which says that there was no error, and so we don't need to correct anything. And because of that, it looks like this little identity matrix inside of this block that corresponds to the code space. And this arrow just shows what this Krauss operator does to a quantum state. It just keeps it in that code space. And we can write out all of these operators, and you see that they all have this nice structure that they look like transition matrices that essentially just implements transitions of the state from the corresponding error space back to the code space. For example, this one moves the state from the subspace C1 to the code space. This one moves from C2 to the code space, and so on. Importantly, when these transitions happen, they isomorphically map the basis from the error space to the basis of the code space, as you see from this sort of these notations.
I didn't get that. Could you try again?
I think my Siri just got activated. Alexa, whatever this is. Sorry. So by looking at these arrows, we can see that this process of error correction is essentially equivalent to artificial dissipation. And in this example, this dissipation is maximally efficient from the perspective of entropy removal from the system, because it corrects any error in a single application of this channel. But it's not the only way how you can do error correction in this system. And so here's another way, another kind of dissipation, basically. We call it trickle-down dissipation. So in this case, there are only 2 Krauss operators. So this K0 is the same as before. So its interpretation is that there is no errors, so no worries. And then K1 transfers the quantum state between the neighboring subspaces. So it goes from C3 to C2, C2 to C1, C1 to C0, and all of these transfers are happening at the same time. So you can see that also from this kind of off-diagonal structure of this transition matrix. And in terms of these arrows, that means that all of these 3 errors are happening at the same time. So this is a quite unconventional approach, but it has the capacity to correct all of the same errors as the previous stabilizer approach. It's just not able to do so in a single step. So in this sense, it's not maximally efficient from this perspective of entropy evacuation. So for example, if the error throws your state into this last subspace, then it will take 3 hops to completely correct this error. And so because of this property, this approach is natural if your errors have some kind of hierarchy. For example, when this error is much less likely than that one. Repetition code a priori doesn't have this kind of property, but we will see later that the system, our system does have it. Okay, so what are some other nice properties of this approach. So it can be extended to arbitrary number of subspaces. You can just imagine stacking more circles to this chain and just increasing the size of this matrix. And so that means that we can correct many different kinds of errors with only 2 cross operators. And this is a very nice property because such channel of rank 2 can be implemented with a single ancilla qubit. And I already showed you before the picture of this ancilla qubit in our setup, which is the transmon. And the reason we are talking about this now is because the QEC scheme that the QEC circuit implements in our case is actually more similar to this trickle-down approach than to the stabilizer approach from before. But instead of this linear chain of these error spaces, we have a structure like this. So at the bottom here is the code space. So what you see is a density matrix of a fully mixed state in the code space. So it's just an equal mixture of 0 and 1. And these are the first 2 error spaces. So if you look inside of this black circle, you'd see the difference between them, that the red is biased sort of away from the center here and towards the center in this case. And we can ask which errors generate these subspaces from the code space. And the answer is it's a photon loss and photon gain of the oscillator. And you can probably guess what these next levels in this hierarchy are. They are double photon loss followed by photon gain, and double photon gain. And it's a nice and simple structure of these error spaces. And it has this property that I alluded to previously, that the errors in these higher levels of this hierarchy are less likely than the errors in the lower layers. And so because of this, we can use this trickle-down approach to error correct these states. So I hope this answers one of the questions that came up earlier about what kind of errors the circuit is correcting. So these are the errors. So now let's look at the Krauss operators. So again, they are shown here as matrices that act on the quantum state. And they are written in a special basis that splits into these pairs of states, which form orthogonal subspaces. And all of these subspaces are the replicas of the code space. So this Krauss operator KGG is diagonal in these subspaces. And within each subspace, it's off diagonal. So this is kind of a funny, weird feature, and it's because our QC circuit applies a deterministic flip of the Pauli frame in every cycle. So it just deterministically flips 0 to 1 and 1 to 0 in every cycle. And that's not a problem because it's deterministic, so we can account for this. And so when we get this outcome GG, then you should think that this matrix just multiplies your quantum state. And then the state will remain in the same subspace where it was, so no errors would be corrected in this case, as I'm also kind of showing with these arrows here. And then also you can see by the color of this matrix element that this outcome is the most likely to happen when this quantum state is in the code space to begin with. And then these other matrices that contain one or more E outcomes, they implement transitions between subspaces that overall dissipate the quantum state down towards the code space. These they have this nice block structure where I'm highlighting the blocks with these black rectangles. And because of this block structure of these matrices, we have a tree structure of the error spaces like this. And so this thing at the bottom corresponds to that block. These two subspaces correspond to this block, and so on. And so these two matrices here implement transitions between the neighboring levels in this hierarchy. So they just drive everything one level down. And then this Krauss operator implements transitions 2 levels down. So now that we've seen these matrices, let's consider just a few examples of Monte Carlo quantum state trajectories that are induced by the dissipation and by this QEC process. So here is a quantum state. It's written as a vector in this basis that we just used before for the Krauss operators. So think about different vertical slices on this plot as just quantum state vectors at different times. And time, of course, runs horizontally. So at time 0, you see that there is only one component of this vector, which means that this state is initialized as one of the logical states. And then as time goes on, and the time is measured in cycles here, this state just keeps flipping back and forth because of this deterministic flip of the Pauli frame that I mentioned previously. And in this particular trajectory, there are no errors. So the state remains always inside of this code space. Also, you can see that by these measurement outcomes that are always green, and green stands for the G outcome. So that indicates that no errors were corrected in this particular trajectory. And then in this next example, we initialize the state in the same way as before. And then we, at time 0, we inject this photon gain error. And you see here that this error kicks the state out of the code space into this second error space. And then right after this error happened, it gets immediately corrected by the QEC process, which is also accompanied by this emission of the EG outcome. And then afterwards, the state just remains in the code space. Also here you see the fidelity of the final state to the initial one, which is really high. So that means that this error is corrected very well by our approximate circuit. And this is an alternative scenario where the same error was corrected not immediately, but only on the third cycle. So basically the state has spent some time inside of this second error space, but it's not a huge deal because this subspace is a replica of the code space. And so these are two different possible trajectories that correct exactly the same error. And as I showed you before, when I introduced Krauss channels, we can calculate the probabilities of any such trajectory, but we just cannot predict in advance which trajectory will actually be realized. And this is where I want to quote Alexander Korotko here, who once said that in quantum mechanics, you don't see what you get what you see, which is very deep. And anyways, so this is the last example where a more serious error happened. And then when it was corrected, it generated this kind of trace of measurement outcomes. So these pictures here, they are Monte Carlo simulations. And in experiment, we don't actually have direct access to the quantum state in every trajectory. So we can't actually see this. But what we can see is these measurement records. So they inform us which path the system has taken. And so let's look at some real measurement records from the actual experiment.
Sorry, quick question. What's the difference between KEG and KGE? Because in the previous slide, it looked like they kind of correspond to very similar trickle-down processes.
They are very similar indeed, but not the same. So this channel in this sense is nearly degenerate. So it's almost rank 2, but it's actually rank 4 because they are different. It's just imperceptible difference.
So they take the same error spaces down. They take the same spaces to the same spaces, but maybe with like a change in phase or something, or slight difference in magnitude.
Yeah.
Okay.
It might be that like the fact that they are so close results from this approximation that we use for the circuit, that just 4 layers.
Mm-hmm.
Maybe if we increase the accuracy, they would degenerate into the same Krauss operator. I'm not sure about that, to be honest.
Okay. And these Ks that you're applying, this is the result of measuring some syndrome, and then what you decide to apply afterward is this K operator. This K operator isn't, I guess, what's happening as the error is happening in the first place. It's like
yeah, you're right. So this K is made up of, it's a composite effect of the unitary circuit and the feedback that we apply in the end. So all of that together is combined to produce these K operators. But of course, they don't know anything about the errors. The errors happen stochastically, and we have no control over those.
Got it. And then in your next slide, where you show, your wave function psi, and you apply some a dagger or a double dagger or whatever, that's basically going from these green bubbles up to some orange error space bubble. So it's kind of like a reverse process of these Ks.
Sorry, say it again.
Your errors here, so these a daggers, these a double daggers, in your previous slide where you show the different spaces and this trickle down, it's basically just the reverse process. You were going back, we're going up.
Oh yeah, exactly. So when I apply this error, you see from this kind of state vector that it kicks you into a second error space. So that means on this picture that you're just going from this error space into this one.
Okay, great, thank you.
Yep. And then error correction takes you back down.
Cool. Yeah, thanks.
Okay, so now here's the sample of these measurement records. So here, this vertical axis is time measured in cycles. And I think it runs here to 1000 cycles. And we just stack different shots of the experiment along this horizontal axis. And then the green means that it's a G outcome of the ancilla measurement. Yellow means the E outcome. And then red means the leakage outcome. So what do we see? So green indicates that no error was corrected in that particular cycle. So to remind you, this is most likely to happen when the state is in the code space already. And then these other outcomes that contain an E indicate that some error was at least partially corrected in that given cycle. And for example, this long string of E outcomes signals to us that there was some pretty big error here that took a lot of time to handle, a lot of time to dissipate the state all the way to the code space. And sometimes there are these isolated leakage events, which are marked red. And if this leakage is to the F state, which is the next state in the transmon after the E state, then our protocol will actually reset it back to the ground state. But if this leakage is to a higher state, then our current version of the protocol can do nothing about it. So the ancilla will be just stuck in that state for a while until it just randomly decides to fall back to the computational manifold of states. So next, if we average all of these trajectories together, so average across this axis, we see that the probability of getting a G or an E outcome is nearly constant in time. And this is evidence that this process of basically jumping back and forth between these different error spaces is indeed a stationary stochastic process. And notice that there is an axis break here. And this process actually runs up to 100,000 cycles, which is around 1 second of time. And the probabilities of these different outcomes remain constant throughout this whole run. And so this code really is stabilized. Its envelope doesn't expand slowly and indefinitely, and it doesn't shrink to vacuum eventually, and these error rates don't increase over time. So that's a really nice stability. And this plot only shows the average, but we can actually analyze other statistical properties of these strings of measurement outcomes and extract a lot of information about this QC process. And so some of these two important figures of merit that I want to highlight are the probability of occupying the code space in this kind of dynamical equilibrium is about 80%. And the rate of getting excited out of the code space is about 13% per cycle. So this 13% it's an aggregate error rate that indicates all kinds of errors together that take the state out of the code space to any of these higher error spaces. All right, and so so this sort of data looks exactly like what we expect based on the Monte Carlo simulations that I showed you before. But we need to confirm that when we see these kind of speckles of yellow in experiment, that really means that some errors have happened and that they were corrected afterwards, and that this is not just some sort of random number generator that we hooked up to with our experiment. And so we can, to verify this, we can do the following. We start each of these trajectories by preparing a logical state in some Pauli basis, and then we run this experiment, do all of these measurements, and then in the end, we measure the state in the same logical basis as where we prepared it to see if it's the same logical. And then we obtain some sort of decay curve like this. So here it's showed the lifetime of, you see a decay of Y state and of the Z state. And so if these yellow dots are really correlated with occurrence and correction of errors on the GKP state, then we would expect that trajectories with less yellow preserve the quantum state better. And we can verify that by doing post-selection. So in this post-selection, we just look at a trajectory and identify if it has a pattern like this with many repeated E outcomes. So the more E outcomes it has, the more likely it is that the state got corrupted eventually. And so let's use the following post-selection rule. So if this trajectory has a pattern like this that repeats D times, then we just trash it. And so if we look at case D equals 5, then we find that this decay become milder. So we go from this decay curve to that one. And also we get a slight improvement in this post-selected lifetime. And then as we progress towards the most stringent post-selection case of D equals 1, which means that every trajectory with even a single yellow E outcome is trashed, then the decay curve improves quite significantly. So we go from this to that, and the post-selected lifetime in this case becomes 10 milliseconds. But we throw away trajectory at a high rate of about 10% per cycle. Okay, and so this post-selection experiment just performs an important check that these measurement records indeed indicate the occurrence of errors and the occurrence and correction of errors. And then in this panel, what we see is the decay of the logical fidelity of some selection of states. And now I want to show you how the actual quantum state decays and changes over time. So this can be measured with the quantum state tomography using the Wigner function. So here, this top row is the logical 0 state, and the bottom row is logical 1. And in this direction, we have time. The time starts at 0, so 0 cycles, 0 milliseconds, so basically no error correction here. And then it runs up to 800 cycles, which corresponds to 4 milliseconds. So, so these are the states right after initialization. And you see that they're slightly distorted. So that indicates that our initialization is not perfect. But then these distortions quickly get corrected by the QEC process. And when we reach 100 cycles, everything is already very nice and square. And then over time, this pattern that indicates which of these two states we are looking at, it gradually disappears. And then after 800 cycles, we almost can't distinguish them anymore. So this is precisely the process of logical decoherence. And so we can ask what quantum channel describes this logical decoherence. So it's called a Pauli channel. And in contrast to channels like amplitude damping, which would drive the qubit to one privileged state, which is the ground state, this Pauli channel just mixes these two logical states, 0 and 1, together. So we can see that very explicitly at this bottom panel. So this bottom panel shows the integral of the Wigner function along the momentum axis, which gives the probability distribution of the position of the oscillator. So this measurement here, it's literally an absolute value squared of the wave function. And so I showed you the cartoon of this wave function before, but this is the real measurement of it. And so anyway, so right after initialization, you see that these 0 and 1 states, they're nicely separated. And then as time goes on, each state starts to acquire these peaks in the locations of the opposite state. And then these peaks, they start growing, and then eventually these states become mixed together completely and become indistinguishable. So at this point, all of the logical information is lost, basically. All right, so now we come to the last slide, which illustrates basically the most important achievement of our experiment. So throughout this talk, I showed you different bits of data that just build up a coherent picture of what's going on in the system. But ultimately, what we really wanted to show is the demonstration that we can put together imperfect quantum components and then do some imperfect operations with them, and as a result create an active qubit which is more coherent than everything that we started from. And this is basically the data set that quantifies how far we managed to get in that direction. So here we compare the lifetimes of different passive qubits that can be created in this system to the lifetime of this error-corrected GKP qubit. So top panel shows the lifetime of the qubit created using the lowest 2 energy levels of the transmon. And the middle panel shows a similar qubit, but created using the lowest 2 energy levels of the cavity mode. So to remind you, this is the best passive qubit in our system. And the bottom panel shows the GKP qubit. So these empty circles here, they show how this qubit decays in the absence of any error correction if we just prepare it and let it be. And you see that it dies off even faster than the transmon in this case. And then the filled circles show the decay in the presence of error correction. And by comparing these 3 plots, or if you want, you can also look at these numbers, it's clear that this error-corrected qubit lives much longer than all of our passive qubits. And by repeating this experiment for 6 different cardinal points on the block sphere, we can extract the rate at which the average channel fidelity decays, and then compare this in this little panel here, from which you see that basically the error correction gain in our experiment is equal to about 2.3. Okay, and so that brings me to conclusion. So please check out our paper if you want to learn more details. And thank you so much for your attention. If you have any remaining questions, I'd be happy to answer them.
Great. Thanks, Vlad. Thanks for the really great talk. I think during the talks, people ask questions. I try to pass them on. I actually have a couple more that I wanted to ask. I won't go too long because I know we're over time here. The first question I have is this reinforcement learning algorithm. You said it takes 15 seconds a cycle. It seems like you do it for a few hundred cycles. And I'm wondering, how long is this like calibrated QEC circuit good for? When does it become stale?
Oh, that's a good question. So it's good for about a week. I know that in some other systems, the time scale of different drifts is faster, maybe like even order of hours. In our case, this cavity mode is pretty stable, and transmon, probably due to the improved fabrication technique, is also pretty stable. And so the calibration lasts a week. Actually, I have a backup slide here that I can show. So this is a repeated measurement of the lifetime as a function of time. So we measure it here for about a week. And this qubit, this QEC protocol was calibrated only once at the beginning of this plot. And so you can see that there is a slow degradation of performance. And on top of that, we have these kind of random jumps because of the spurious degrees of freedom that come in resonance with our processes.
Great, thanks. And did you guys try to hand tune for the QEC circuit and find that the reinforcement learning would just far outperform what you could do by hand?
Yeah, so the reinforcement learning doesn't start from a complete scratch. It starts from a point where we do a lot of individual calibrations of all of the components, which is pretty much like hand tuning. So there are different one-dimensional sweeps of this parameter, that parameter, and then you pick the best point, and then you move on to calibrate the next thing. So that is done initially, and on top of that, we found that we need to throw in reinforcement learning to calibrate everything in this one context together.
I see. That makes sense. My final question is, going back, slide there, you showed the next steps. What in your mind are the hardest things to do to be able to do, let's say, in bit flips, or to be able to do a logical 2-qubit gate?
Right. So this is actually an ongoing work in Michel's lab now to demonstrate 2-qubit gate between these GKP qubits. Well, it requires to be able to couple these cavities somehow. If you want to realize the GKP state in the cavity, it can also be done in 2D. And there are different candidates for this sort of coupler. It can be a circuit that looks more like a transmon or like a snail. There are different kinds of superconducting circuits that you can use as a coupler. One of the big challenges is that for these couplers, we prefer to make them flux tunable for different purposes, and then you need to be able to get the magnetic field somehow into these superconducting cavities, which is very difficult. But yeah, maybe next year there will be a first demonstration of this 2-qubit gate.
Awesome. Well, thanks so much for the presentation. Thanks for coming, Vlad, for a second time. Big thanks to everyone in the audience for tuning in. Like this video, subscribe to the YouTube channel, and we'll see you next week. Thanks.
Yeah, thank you.